All right, let's explore a cubic polynomial that's coming from a geometric problem. That's going to be our goal. Basically, we have some three-dimensional object, a can. We have some constraint on how we build this thing, and we want to um, find out if given a certain volume, what are the dimensions that we should have, given, what is the maximum volume, and yeah, just kind of what it looks like. So here's our problem. We're going to construct kind of a wire frame that we then sort of sheathe in some other material. But the wire frame, we've just got a certain amount of. It's an artificial problem, but whatever. So we've got this height here, and we've got the radius of the base. Now, circumference of a circle. So circumference equals 2 pi r. And so this is for the circle. And the area is pi r squared. And then we've got height h. So amount of wire used. Well, we have both the top and bottom circles. So that's 2 times the circumference of those things. So we just have this wire that goes around the top and the bottom. And then we've got the 2 vertical stands. So you just have this, those 2 kind of poles. So you have 2h. Maybe you add more. So maybe like 4h or 6h, and you can see how that might change the problem. So it's a direction to maybe go. Or maybe add some more layers. Maybe have a circle in the middle. So like there's various different things you can do to change this setup. You could also just maybe have a singular height that goes down in the middle, holding the top and the bottom. Whatever. And yeah, you could do a number of different constructions. This is what I'm going with. Amount of wire used, and then what is the volume? So the volume is essentially you take that surface area at the bottom, and you just kind of think of layering that all the way to the top. And how many layers? Well, that's the number kind of the height. This is kind of a little bit sketchy argument, but hopefully it makes some intuitive sense that you sort of, you've got these kind of slices. So that's pi r squared times h. Okay, good. And so this is 2 variables, r and h. So we need some more information to make it into 1 variable, which is what we're currently talking about, 1 variable. So where do we get that? Well, let's constrain amount of wire used. You could also try to work backwards. You want it to be a given volume, and you find out how much, with the radius and the height, well, how much wire you need. But we're going the other way. Constrain amount of wire used to be, let's just say 10 inches. Let's see where that takes us. Let's see. Well, maybe 20. Let's go with 20. I like 20. 20 inches. 20 inches might be nice. So that means that this is telling us 4 pi r plus 2h needs to equal 20. Or 2 pi r plus h should equal 10. So h is equal to 10 minus 2 pi r. All right? So that's that. And let's see how much so just as an example, if we were to take r equal to 1, then we would get r equal to 1, then h is equal to 10 minus 2 pi, which is approximately, 2 pi is about 6.3, so it's about 3.7. Right? So that's sort of how it goes. All right. So that was just an example to plug it in. So now our volume can be written entirely in terms of r, pi r squared times 10 minus 2 pi r. So that's our volume. All right? And of course you can write that in terms of x. So let's what can we ask? We can ask what should h and r be for a volume of 100. All right, so there's a number of ways of doing this. I'm going to show you, of course, my favorite way of basically guess and check. We'll just do that first with the calculator. So we got pi r squared, 10 minus 2 pi r. So on our calculator here, pi x squared, and then times 10 minus 2 pi r, where we use x. So now we can go to table, and we looked at before, and what was it? R was 1, h was 3.7. So why don't we just see what that is? Okay, 1 gives us 11.3. Let's see what 2 gives us. Negative. That's not looking good. 1.5 in between. Okay, that went down. What if r was 0.5, 0.25? All right, so that's looking like we can't do a volume of 100. So no solution, probably. It looks like, well, let's see if we can graph this thing. Zoom fit. That looks standard. All right, here we go. So it looks like we should be able to get up to, well, there's the max, 11.8. Okay, so no solution. So let's try volume of 100, sorry, volume of 10. All right. Okay, so obviously with this little interface, I can just drag that point and it should be about 0.8. Okay, let's look at the table. So, yeah, so one was almost the maximum. Okay, good. Which we kind of got a feeling for. So let's see, 1.5 went the wrong direction. Well, actually, that's not entirely true, right? As you see here, there's 0.8, and then there's also on the other side something like 1.3. So we can do either side, right? So unlike some of the other problems, you know, you might actually get multiple valid solutions. I guess one needs to check that the constraint makes sense, but probably. Why not? Okay, 1.5. Let's go with the 1.5 thing. So 11.7 and 4. And we're looking for 10. So 11.7 for 6, 2-ish. I'm going to go with being a third. Kind of a third. That's 5. Let's see. I'll just go 1.2. And that's 11.123. So I need to be on the other side of 1.2. I went down 0.5 between 1 and 1.2. Now I want to go a couple more. This is clearly 7, 1.3, 9.72. Okay. And now 1.3, 9.7. That's lower. So let's look at 1.2. So 11.1. Let's just go with 1.27. All right, so that's 10.23. It's a little on the high side. So let's try 1.28. Getting better, 1.29. All right, so it's between 1.28 and 1.29. 1.2. It looks like it's kind of close to 2.8. Let's see, 3. 10.02. 4. 285. Yeah. And, just like that. All right. So we got the formula. We can still try it. It's a little bit more trickier than it was with lines and quadratics. The lines we could do it exactly. Or the guess and check with quadratics because it's steeper, right? Look at this. Look at how steep that is. Okay, not steep when you zoom out that way, but try to have it more or less on scale, it's a very steep change. So that makes it very hard. It's a sharp kind of line going down there. All right, and so that's somewhere like 1.28. So that was R. That leads to an R equals 1.28, and so H is equal to 10 minus that, so 10 minus 2 pi x. So 10 minus, oops, 10 minus 2 pi x times 1.28, say. So it's about 1.95. Okay. So that's how you get particular feeling for this thing. You can guess and check. And so there was also the other possibility. I won't go through the guess and check there, but just to confirm that that made sense too. So that was about 0.8, right? So second, enter. And then 0.80, so 4.97. So that's a very tall one. Or are approximately 0.8, and H is approximately what was it, 4 point something like 97. All right, so kind of yeah, so sort of 5 times 0.8 squared times pi should be about 10, right? R squared 0.8 is 0.64. Pi 0.64 times 5. These are kind of reasonable. Sort of like, sort of like 3 times 5 is 15, and 0.64 is kind of like 2/3, so it's kind of like 10. Well, it seems reasonable. The other one is what, 1.3 and 2. So 1.3 squared. 13 squared is 169, so 1.69 times 2, 3.4 times another 3.1, 9 plus something, so sure. That makes about good sense. It's good to do those kinds of mental checks and computations that they both make sense. So we got positive numbers for both. We got the volume we want it. So that's that. We have 2 solutions. So you can make you can make one with a sort of a fatter base and shorter height, or one that's really long and tiny base. They'll have the same volume. That's the way it goes. And you can kind of think of, if you think of it as like a very wide base and short height, right? It's kind of like there the volume is going to 0, even though it's like very thinned out. And you can also make it very, very narrow. Again, the volume is going to pretty much go to 0. But, and so then you have these kind of 2 sides, and so in between you get what you want. And you know, if we wanted to maximize the volume, then that's what this little graph gives us, right? And you can also kind of fumble around with guess and check, just trying to get larger and larger, right? So everything is stable. So like 1 looked pretty good. So you do 1.1. Oops. So 1, then 1.1, 11.74, so it got larger. 1.2, not so large. So it's somewhere in between those. 1.11, is it going down or up? So it went down from there. So then you go on the other side. 1.09, 1.08, 0.07, 0.06. So that looks like it's kind of stabilizing a bit. Yeah, so that's definitely went down. So now it's like, you know, something like that, right? And what was it? It was, there you go, the max is 11.8 at 1.061. All right, look at this graph. We've got r equals 0, which will give us the height of 10, because volume 0. And then we also have this 0, like so. That happens when the height is 0. And r is sort of the maximum it can be. So that's the 4 pi r equals 20. All right, so 20 divided by 4 is 5. And then 5 divided by pi, I guess. 5 divided. There you go, 1.59. All right, so that's that. Now, of course, you can also do all these things over in GeoGebra. So you can do whatever that formula was, pi x, oops, x squared times 10 minus 2 pi times x. Alrighty, and we get this again. We can zoom out. Oh, right. Let's see what the extremum is. 1.06 at 11.8. And the roots. And notice also that the GeoGebra found the extremum at 0. That's a minimum, which is also a root. All right, so that's how you can play around with the problem. You know, max volume happens around r approximately 1.06, and then h is whatever that is, and you get the volume. So there you go. Now, the finding the volume, the maximum volume, or finding the volume at other places, exactly, these things are not easy. Graphing, tabling values, that's pretty much a good place to go. The couple rules involving like between any two zeros, there should be a max or a min. Basically, the graph has to turn around to get back to the 0, right? So That's sort of one setup. To kind of find it more algorithmically, we would use calculus, which would produce this other function called the derivative, and those zeros would be where maxes are. The zeros of that function would be where the max and mins are, and that function would be a polynomial of 1 degree less. So like here we have a cubic, so then the derivative would be a quadratic, so that would have 2 roots, and that corresponds to the 2 max and min points that we have. Again, that's all part of calculus. But yeah, and it kind of illustrates that even finding the max and mins is essentially finding zeros of something, right? Finding the zeros is important. Oh, I should also mention that. This problem here could be written as, pi r squared 10 minus 2 pi r minus 10 equals 0, right? So just want to emphasize you can always find the value, find the place where it's this value as a problem for solving zeros. Solving zeros is the heart of a lot of the issues and difficulties that we encounter. You can always kind of phrase it in that problem. So that's a good generic problem to understand how to solve.